So welcome everyone to this week's Origins Colloquium. It's a great pleasure to welcome Andreas Kieran back. Andreas, we just met recently in Tucson and connected again, but Andreas leads a couple of groups in the Sternwarte in Heidelberg. So the instrumentation group and the exoplanet group. So there's a number of very important projects that we may hear about now. But Andreas actually started as a radio astronomer doing VLBI. You did your PhD in Bonn, and you've used data from Onslow. So we're happy you had a chance to see the observatory yesterday, although the rain was not the best. Anyway, so I think we're going to hear about the exciting work coming out of the exoplanet work you're doing in surveys, and we welcome you, Andreas.
Yeah, thanks for inviting me here. I'm usually at Heidelberg and taking a sabbatical at the moment. The first part was in Tucson, where we happened to meet, and the second part is at the Danish Technical University, which is close enough here in the neighborhood, so to speak. We drive up for a seminar, and one of the topics that I'm interested in currently is planets orbiting low mass stars. And let's see. How do I advance this? Okay, this seems to be working. Good. So there are several methods to detect extrasolar planets. The one that I am using mostly is the radial-velocity method, and this is probably well known because it also was the first successful method to detect planets around main sequence stars, which was awarded with a Nobel Prize a few years ago. So what's happening is that the star and the planet are orbiting the common center of mass, and that means due to the Doppler shift, all spectral lines, so-called Fraunhofer lines in the stellar spectrum, get blue and red shifted with time, and we are trying to measure these tiny shifts of the lines in the stellar spectrum, and that tells us that the star has a planet. So we look at the star, we never see the planet, we just look at the shift of the spectral lines. So the observable that we get out of that is the mass of the planet times the sine of the inclination angle. If the planet is face on, then you will not see any signal. If it's face on, you will see the full signal, and otherwise it's related to sine I. But if you have randomly oriented orbits in space, the expectation value for sine I is 0.87. So in many statistical analyses, you can just more or less, to first approximation, forget about this sine I problem. The second important method, which by now has found most extrasolar planets, is transit photometry. So this is being done from the ground, but also with space missions. And here, the idea is that if the orientation is favorable, then the planet will be transiting in front of the star, and you get this dimming because some of the starlight is blocked, and also then later the planet will disappear behind the star, and you get the so-called eclipse when the light from the planet is missing. So what you get out here, the observables, are from the transit, you get the planet radius, because the bigger the planet, the more light it blocks. Also, you can try to get information about the atmosphere, because the atmosphere is kind of a ring around the planet that absorbs spectral lines, for instance, of molecules or atoms that are in the atmosphere. So the planet will appear a little bit bigger when the atmosphere absorbs and smaller when it doesn't absorb. Also, if you do infrared observations, then the planet contributes a significant amount of light to the total observed light. So just before it disappears behind the star, there's more light than when it is behind the star. So you get the day-side temperature of the planet out of that. So these are the observables out of transit photometry. And then when you combine the two methods, then you get the mass and the radius, and the mass and the radius give you density and surface gravity. So that combination is frequently interesting because that's the first very rough way of determining what the planet is made of. The density tells you what it is made of. Unfortunately, there are complications for combining the two methods. You cannot just say, for any known exosolar planet, I just do both to combine them. So first of all, not all planets have transit as viewed from Earth. Yeah, if it doesn't happen to be almost in the right plane, then it doesn't transit the star. And the probability for having planets is the radius of the star divided by the semi-major axis of the orbit, or the radius of the orbit. So for the Earth and Sun, that would be 0.5% roughly. Yeah, so 1 out of 200 randomly oriented observers in the universe will see the Earth transiting the Sun. Also, precise radial velocities are only possible for bright stars with sharp absorption lines. So typically, the limiting magnitude of our surveys, if you really want to learn about very light planets like the Earth, not Jovian planets, then we have magnitude limits between 6 and 12th magnitude. And frequently, other techniques look at fainter stars. So for RV follow-up, you really need very bright stars, and we are restricted to certain spectral types. So these are the cooler stars, in astronomy jargon, the later spectral types F, G, K, and M. You can't do this for hotter stars. So the typical strategy that we are using, and other groups also, is we do radial velocity follow-up of transit candidates from space missions. Space missions such as first Kepler and now TESS give us transit signals, and we get a list of possible detections of transiting planets, and then we use a ground-based radial velocity instrument at a telescope, and then do the follow-up to combine the two methods. And for these space missions, there is a trade-off in survey area versus the duration where you look at certain fields. Ideally, you would want a space mission that looks at the whole sky all the time. Of course, this is not quite possible, so different missions have adopted different strategies how to compromise. The Kepler mission had just one field in the sky that it looked at for a very long time, for 3 years. And that means it saw planets also with relatively long periods of up to a couple of years, but only a few in the sky, and only a few always mean that you do not have very many that are very bright. So the TESS mission was built to be complementary to that, and that looked, or is still looking, it's still working, it's looking at the whole sky, or almost the whole sky, but only each part of the sky only for a couple of weeks. So you get planets with short periods, you get them all over the sky, and that means you get the brightest objects in the sky, but you do not get very long period planets. And now Europe is building the Plato mission, which will be launched end of next year, or maybe in early 27. That is kind of in the middle of this parameter space. It will be a larger field than Kepler. It will also be a long time, and it may also then have a second phase in the mission that is more similar to TESS. So the goal here is to have planets that have long periods, like the ones that were discovered by Kepler, but that will also be brighter because it has a larger field. It sees more of the bright stars that are easier then to follow up with radial velocities. There's a certain opportunity for M dwarfs, which are the coolest and smallest stars. First of all, M dwarfs have a huge mass range. M stars as a spectral type, they range from the hydrogen burning limit at 0.08 solar masses all the way up to 0.6. And covering a large range in masses is a good test for planet formation scenarios. Also, detecting and characterizing terrestrial planets is much easier for M dwarfs than for more massive stars. And this is because the transit depth of course, depends on the stellar radius. And for a G star, an Earth makes a transit of 10 to the minus 4, but for a late M star, so the coolest stars, it's about 1%, so the signal is much higher. Also, the radial velocity signal is related to the mass of the star, so it gets larger for a M star. It's about 1 meter per second for an M star, but only 10 centimeters per second for a G star. So for astronomers who are used to thinking in kilometers per second or hundreds of kilometers per second, these are really tiny velocity shifts that we are trying to measure. Also, if you talk about habitable zones of these, when we talk about terrestrial planets, we are usually interested in the question of, are they habitable? And in a very coarse sense, habitable, the first thing that we normally consider is the temperature suitable for liquid water at the surface? Then these habitable zones are close to the star, which means the orbital periods are close between only 10 and 30 days. So this is also good for detection, which makes so M stars are really easier. But there's a high ratio of the ultraviolet flux to the volumetric flux. So talking about whether liquid water is possible, you're interested in the volumetric flux, how much energy do I get to heat the planet to a certain temperature? But then the atmosphere is very much affected by UV radiation. And M stars have long lifetimes as young and active stars, up to several giga-years. And so there's the danger that the atmosphere will be completely eroded by ultraviolet radiation. And there are many unknowns. Yeah? So we don't really know what the UV emission is over the full stellar lifetime. And we don't know much about secondary atmospheres from outgassing and so on. So we really don't know whether planets of M stars can be really habitable in the sense that they are good for life. So we built an instrument called CARMENES that is addressing these questions. And the acronym is really quite complicated, but it's also a summary of the talk, so to speak, because we are located at Cala Alto Observatory, which is in southern Spain. We work at high spectral resolution. We are looking at M dwarfs. We're interested in exo-Earths. We do this in the near infrared and the optical. And the instrument is a shell spectrograph. So it's a German-Spanish consortium. And so when we started this some time ago, the first question we asked, in which wavelength range should we observe? There were some instruments that existed at the time. This was pioneered in France and then at ESO with an instrument called HARPS. And typically, these instruments worked in this wavelength range. And you see, this is the energy distribution of typical M star. You don't get very many photons here. So we said, here is where most of the energy comes out. And so if possible, we really want to observe in this wavelength range. We should build an instrument covering this wavelength range. But there are two things that are important if you want to build such an instrument. First is, where do I get most of my photons? And the second question is, where is most of the information in the stellar spectrum? Because if the stellar spectrum is kind of flat, you don't get any radial velocity information. You need a sharp spectral line to get information out of it. And so it's the combination of many photons and many lines that makes a certain spectral range good or not so good. So we didn't know very well where that was. So we built an instrument that actually has two spectrographs, one working in the visible, one in the near infrared. Both are coupled by fibers to a front end. The front is attached to the telescope, so light gets in here and gets sent to the two spectrographs with proper calibration and so on. So this is what the spectrographs look at. They are in vacuum, they are temperature stabilized on the millikelvin level because we really want to be very stable. We have one working in the red part of the optical. The blue part is not interesting for us because the M stars are too red for that. There's one working in the infrared, and we got the best detectors we could get 10 years ago, and we installed this at this 3.5 meter telescope in southern Spain, where it has been working now for about 8 years. So this is kind of what we get out. These are, well, we put on nice colors. Of course, these colors are kind of fictitious. You just get intensity as a function of wavelength. What you see here, this comes from the visible spectrograph. The upper part comes from the infrared spectrograph. And we take the spectrum and this type of instrument, which is called a cross-dispersed shell spectrograph, that puts the whole spectrum in this kind of interesting format by having a grating that disperses in one direction and a low dispersion in the other direction. So blue starts down here and it runs, the wavelength runs in this way, up and up in this way from the blue part to the red part of the spectrum. And if we zoom in here, this is the stellar spectrum, and you see some stellar spectral lines on the stellar spectrum. And down here is a calibration or calibration source. So each line here has information about the radial velocity shift of the star. And the challenge is we have to measure any small shifts in the stellar spectrum relative to the calibration spectrum. And the precision that we want is, if we want a meter per second, it means we want a shift of 1,000th of a pixel. Or in physical units, this is something of order 10 nanometers. Or you can also say we want to measure shifts of the spectrum on the detector by 10 silicon atoms. So we have the CCD, and if the spectrum moves by 10 silicon atoms, we have detected a planet. So this is an enormous challenge for the stability of the instrument and the calibration that we put on. This is the technical difficulty in doing this.
What is your calibration source?
Oh, this is a Fabry-Perot etalon. And we calibrate the FP etalon, which doesn't have an absolute standard, against hollow cathode lamps that tie this to atomic lines. Yeah, so this is a plot showing relative precision that we get in these different wavelength ranges. So initially, we didn't really know what is the best wavelength range. So we played it safe and built these two instruments. And it is clear a priori that for a blue star, the blue spectrograph will do better than the red spectrograph. And as you go to cooler and cooler stars, the blue spectrograph will get worse and worse, and the red spectrograph will get better and better. And we thought that for stars with spectral types, something like M3 to M4, the both of them would be equally good. And for the later stars, the infrared spectrograph would be better. For the earlier types, the visible spectrograph would be better. But we didn't really have enough data to be able to say that beforehand. When we looked at our first data, we saw that this crossover was not really at M3 to M4, but cooler stars, M5. So this is kind of shown in this spectrograph for an M5 star. This is the precision that we get out of the blue. This is that we get out of the red, and you see blue is more precise than red. So these are the data in kind of order by order, and these are binned, and these are even more binned to show how the different spectrographs are doing. So, and the reason for that is that we didn't know enough about the molecules in the spectra. It turns out that in the red part here, there are the information of the radial velocities comes mostly from iron hydride, FeH, and those bands are somewhat weaker than our models had predicted. And the information here comes from titanium oxide, and these are better than we had predicted. So we are doing better in this and not as good in the red as we had anticipated. So in the end, after we knew all this, we are almost always using, for these radial velocities, we're only using data from our visible spectrograph. And for very, very cool stars, the infrared actually gets better, but there are hardly any stars that are so cool in the sky that are bright enough for us if we do half-hour observations. So that's a lesson learned. The first lesson we learned. Then one of our problems, in addition to having a very stable and precise instrument, is things that happen on the stellar surface. For instance, if you have a spot and the spot is on a rotating star, then it moves across the surface. And the spot does two things. First of all, if it's a dark spot, there's less flux coming from there. And so first, the spot is on the part of the spectrum, or part of the stellar surface that comes towards you. So this is blue shifted. And so it blocks some of the blue shifted light, which means the whole line is red shifted a little bit. And later it's blue shifted a little bit. And also there's convection on the whole surface of the star. And when there is a spot, it affects the convection. There are magnetic fields that are stronger, so the convection is not quite as strong. And the net effect of convection is always that you get a bit of blue shift because the hot material is coming towards you in convection. There's a blue shift. And so the convective blue shift gives another redshifted signal. And so together, if there's a star spot coming across the surface of the star, you get an effect that we have to consider, and that may mimic the presence of a planet. So here is some information about the stars that we are looking at. So the total, we defined a sample of stars of 360 stars. We are really looking at nearby stars here. The average distance is 13 parsecs. So these are really the closest stars that we know in the solar neighborhood, unlike some other methods that are looking at planets that are more hundreds of parsecs. And we tried to put our sample together in a way that we cover all subspectral types in this M class. So one of the stars that we looked at is Tegarden star. So this is a really low mass star, less than 0.1 solar mass. And we found two planets orbiting this star, one with a period of 4.9, the other one with 11 days. And they are in the habitable zone of that planet, of that star, which means their surface temperatures are very close to that of the Earth. So if you put known planets in this diagram, where here on the x-axis you have the insolation, so the amount of energy received in units of how much energy does the Earth get from the sun, and here the stellar effective temperature. The Earth, of course, is at 1 in the insolation and the 5,800 Kelvin for the temperature of the sun. Then the two planets around this star are very similar in insolation, but of course the star is very, very different. But depending on how you define similar, these are amongst the planets that are most similar to the Earth of all of the known planets. So here some statistics. So we took 15 stars. This is all the stars that are bright enough for us with a 3.5-meter telescope and this instrument to get good data on in the Northern Hemisphere that have masses that are less than 0.16 solar masses. And so we looked at these 15 stars, and each gray point here is a planet that we found. So this means many, many of these actually do have such Earth-like planets. Yeah, so here is the mass scale. Here's 1 Earth mass. Up here at the top is 10 Earth masses. So all of these planets are 3 Earth masses and lower. Most of them are around 1 Earth mass. And in the background, from simulations, we get our detection probability. So yellow means we can essentially find any planet that is there, and black means we have no chance. And so the periods range from 1 day to 100 days. The this background is then used to kind of correct our detections. If you have 50% chance, you should multiply a detection by 2 to get the actual number of planets that are there. So if you do that, we can do detection statistics. And we did this with different methods. So let's just look at one line here between, say, half an Earth mass and 3 Earth masses. Between 1 and 10-day periods, we get about 1 planet per star. And between 10 and 100 days, we get another. So statistically speaking, for these very low mass stars, up to 0.16 solar masses, you have about 1 planet in this mass range around 1 Earth mass in between 1 and 10 days and 1 between 10 and 100-day periods. So these planets are really very common at these very low masses. Also, here's another star in our sample, JWST, and there are 3 planets in this star, and there is a double resonant chain. So they are in 3-to-2 resonances, and there's a double chain of these resonances. You may know about a very famous system called TRAPPIST-1 that was discovered with the transit method, where you have many resonances. And some people say this TRAPPIST-1 system is very unusual, very rare. We are very lucky to find it. I'm not so sure about this. Maybe this is completely normal for these low mass stars. You have many systems that have resonant chains. We are lucky in this TRAPPIST-1 case in that we are in the right orientation to see transits. Yeah, it is special in that it's very bright and we see transits. If you don't see transits, these resonant chains are much, much more difficult to find with the radial-velocity method. But maybe they are common also, because here's an example that is also one of the brightest stars in the sky that has a very similar phenomenon. Also, if you look at systems of low-mass stars, here's this famous TRAPPIST system with many detections from transits, but there are several other multiple systems, and here's this JWST. Here are the 2 planets around Teegarden star that I showed before that we found in Teegarden star. Now we found a 3rd one in the same system. So there are also at least 3 in that. And with the radial-velocity method, you don't get all the planets at the same time. Yeah, when they transit, normally you see the transits from all the planets, you get them all at the same time. Radial-velocity is frequently one of them has a nice clean signal, and then the next one has a smaller signal, which is more difficult to detect. So you get more data, you see the second one, you get even more data, you see the 3rd one. That happened here. We published 2, and then a couple of years later, with getting more data, we can publish 3. We still see that there may be something more in the system. And if we play a little bit with what our data could be, but we are not sure enough to publish, and there's actually a possibility that these 3 are also part of a longer chain that is a resonant chain. So we need to just get more data. Yeah, so these 3 planets are already 400 data points. Yeah, so each data point is 10 or 15 minutes at the telescope. So it's a lot of telescope time going into these. And we need a lot more to get perhaps more information about these chains. So take-home messages here are almost all of these low mass stars do have terrestrial planets. They have a very steep mass function. There were hardly any planets in my diagram that are more than 1 Earth mass, but if you are sensitive enough to find them 1 Earth mass planets, you find a lot of them. So it's a steep mass function above 1 Earth mass at least. Multiple systems are also probably the rule rather than exceptions, and even resonances may be fairly common. So here's a diagram showing planet mass as a function of stellar mass. Yeah, so on the x-axis is the mass of the star in units of solar masses, and here planet mass in unit of Earth masses on the y-axis. All the red and blues are from our instrument, from ours. The red are from our survey, and the blue are where we followed up on TESS. And I talked about those planets that are in the bottom left corner, but there are also some that are up here at a very low stellar mass, but pretty high planetary mass. So these are 100 Earth masses. So these are Jovian planets. So they are not very common. There are just these two in this plot here right now. We are preparing a paper where we have a few more. But clearly, the message is some planets exist that are rather massive, close to Jupiter, even when the stellar mass is very low. And that's kind of interesting from the point of view of planet formation models. So here are our data showing nicely the signal from two planets. Then the stellar mass is very low. The planet mass here is 0.4 Jupiters. And here are some simulations that simulate on the right-hand side, where you simulate the outcome from pebble accretion models for planet formation. So the black points are what comes out of these models, and the yellow stars are our planets that look like these. So the planet formation models do not really produce such planets. And it's a bit of a mystery where these very massive planets around very low mass stars actually come from. How do you make them? Maybe there's a different formation mechanism for all these terrestrial planets and for these more Jovian planets. Maybe these planets, the black dots in the simulations, come from pebble accretion, and the stars or planets that we find here come from direct collapse of the disk or some other mechanism. That's open at the moment. So this is message number 2, that these Jovian planets around low mass stars are not common, but they do exist, and they are not easily made by those standard formation models that are based on pebble accretion. We are now in the situation, especially with this combination of the TESS mission at our radial velocities, where we can draw diagrams in which we plot the planet radius against the planet mass, and we can compare that with compositional models of the planet. So the black line here that nicely goes through the data points in the low mass regime, this is an Earth-like composition, and the blue line adds 50% water. So this tells us that in the low mass regime, up to 3 Earth masses or so, almost all planets can be modeled by pure rocks. And then above about 3 Earth masses, then there is kind of an ambiguity. You get two kinds of planets. One are bare rocks still, and others are bigger, and they could have a lot of water in them. Alternatively, they could also be rocks with a lot of hydrogen-helium atmosphere above them that cannot easily be distinguished. And if you look more closely at the diagram like this, the data points down here below 3 Earth masses, they really need a composition that is quite like the Earth. So this greenish line here is the Earth composition that is consistent with the data. The orange line down here, that would be 100% iron, clearly doesn't match. And the reddish line here would be 100% silicates. And also this is higher than most of the data points. So it seems that we are now close to the point where down to about 1 Earth mass, we can really say what is the composition. And here we see that it's like the Earth, or perhaps a bit on the silicate-rich side, but certainly in almost all cases, it's incompatible with composition being pure iron. So message number 3 is that for these M dwarfs, we can now measure densities with about 20% precision or so, down to 1 Earth mass, and most of these planets have kind of an Earth-like composition that we can measure directly. So finally, I wanted to come back to atmospheres. And one of the nasty things about these M dwarfs is they tend to be very active and flare a lot. So here's a TESS light curve again from one of our objects, and one sees this periodic modulation. This periodic modulation is because the star has spots and is rotating, but every once in a while it gets really, really bright. And these are big flares. So in these M dwarfs, a star can get, so this is from 1 to 1.8, so it gets almost twice as bright when it has a flare. Now imagine the sun would all of a sudden be twice as bright in integrated light when it has a flare. And we happen to get some spectra shortly after one of these flares. And in the H-alpha line, in this flare, we see a big blue wing of the line. And blue wing means there's a lot of material coming towards you. So this also means that probably this flare was associated with a big coronal mass ejection. So it's not only radiation, but it's also particles coming towards you in this case, or towards the planet, if the star has any planet. So the question is, can these planets have atmospheres, and can they survive such things? Yeah, there was a very nice paper by Laura Kreitberg and others a few years ago who looked at a similar object and concluded that it doesn't have a thick atmosphere. And the way these measurements are done is this can be done in the infrared with Spitzer, or now with the James Webb Space Telescope, by looking at the night side temperature of the star. No, sorry, this is the day side temperature of the star. The day side temperature of the star that you can measure from the eclipse depth depends on whether the star has a atmosphere or not. Think about the difference of the Earth and Moon. We have the same distance from the Sun, but the Earth has a dense atmosphere, so the contrast in day temperature and night temperature is mitigated by the fact that the atmosphere is redistributing energy around our planet. The Moon doesn't have that, so it has a much, much bigger difference between night temperature and day temperature. And by measuring here the day temperature of the planet, in this case, this team concluded that the planet doesn't have an atmosphere because the day side was so hot. If it did have an atmosphere, it would transport away some of the energy, and the day temperature wouldn't be quite as hot. So depending, this is a theoretical diagram showing how deep this eclipse would be, which measures the day side temperature as a function of the pressure in the atmosphere. And this is the basic idea now for a big project that will be carried out with James Webb Space Telescope in the following years, which is called the Rocky Worlds DDT study. DDT means Director's Discretionary Time. So the Space Telescope Science Institute director decided this is the thing that they want to do with the James W telescope in the next few years, and try to measure this, what is sometimes called the cosmic shoreline, that is the dividing place between, on the other one hand, objects in which atmospheres are very likely. That is, these are objects that have a high escape velocity and low insolation. Yeah? Not a lot of radiation that can evaporate the atmosphere, and a lot of gravity and high escape velocity. So these are objects that have a high probability of having an atmosphere, and these are some that have low probability. You can see here are some solar system objects. Earth is just sitting here where it has a nice atmosphere, and Mercury is in this regime where atmospheres are not very likely because there's a low escape velocity and is much more irradiated. And so this cannot be done nicely, of course, for the solar system, for the planets and moons. And now we want to know this for extrasolar planets, and JWST is going to try to do that. And these are all M dwarfs, and a number of these objects in this diagram are the ones that I described before. So this is kind of a next step in follow-on on learning more about these planets. So come to conclusions. Presently, transit missions and our velocity instruments can find planets with one Earth radius, one Earth mass. If the stellar mass is low, there are about 2 such objects per star. The densities are consistent with what we learned with the Earth's composition. A fair number of them may live in relatively closely packed and resonant systems, and we may actually relatively soon find out whether they have atmospheres or not. And finally, Jovian planets challenge formation models, so that's for the theoreticians to ponder more about. Thanks.
Great, thank you very much. Great, then. So we have time for questions and discussion. I'm trying to monitor everything here. So let's see if you're on Zoom, just raise your hand and I'll try and see it. You should pop up to the top, but do we have questions now here? So please, Israhi.
This is more about the instrumentation, but what coolant do you guys use?
What?
What coolant do you guys use?
Good. Oh, we use nitrogen, and we have a somewhat unusual system in that we do not have a real fire start, but we evaporate the nitrogen and do this with gauges, but from a liquid nitrogen preparation unit.
And then furthermore, why do you guys use CCDs instead of like CMOS detectors? Is there an advantage to one or the other for this method?
Yes. CCDs are in many respects much better for astronomy than CMOS detectors because they are much more uniform in their properties because all the charges go through the same amplifier. There are less pixel-to-pixel variations than on CMOS detectors. Also because you spend a lot more effort on the amplifier, the noise can be made lower. We are looking now at the possibility of using more CMOS devices than we used to, and there are difficulties in adapting to the CMOS technologies, which have different challenges. They also have advantages. The infrared detectors that we're using are hybrid detectors, which in some respect then are more similar also to the CMOS detectors.
Mm-hmm. Well, let me follow up on the instrumentation in general. What is setting your noise at the moment? Is it stellar activity, or what's going to happen with the ELT? And perhaps you can say a little bit here about what's happening to improve things.
Yeah, so the stellar noise is kind of a fundamental issue, and the M stars are somewhat worse than G and K stars in that they tend to be more active. So we know that if we don't have a specific mitigation strategy and model the stars, then we are limited to something like, on average, 2 meters per second for each individual measurements by the activity of the star. If you take a very quiet G or K star, the noise from the star may be a little less than 1 meter per second, but around the sun, the Earth would be 10 centimeters per second. So we really have to deal with this stellar noise issue. That is no question. And then getting a spectrograph to work in that regime is a real hard and expensive work. But so far, at least technically, there are probably no showstoppers that would prevent us from going to 10 centimeters per second. It may mean spending even more money on thermal insulation and stability and characterizing the detectors even more. So certainly characterizing the detectors is one of the big tasks. Mm-hmm. And also, not only the spectrograph has to be stable, also the way of coupling the light into the spectrograph has to be very stable. So there are lots of tricks that you can play and need to play with the fiber input into the spectrographs, for instance.
Mm-hmm. So what is the next step to move to an 8-meter class telescope, or is the ELT relevant?
Okay, so as in most of astronomy, the gold standard is always the photon noise limit. You can never beat the photon noise, the Poisson noise from the photons arriving. So when I say, for instance, here we could observe 15 of these low mass stars, that means we are actually hitting the photon noise limit of the number of photons that we can collect with a 3.5 meter telescope in half an hour. If you go to an 8 meter telescope, of course, then you can go to fainter stars if you also invest half an hour. In that sense, trying to go for lower masses where you need higher signal to noise, in principle, the mass that you can detect is inversely proportional to the signal to noise, and the signal to noise is proportional to the square root of the observing time. Yeah, so if you want to go from 1 meter per second to 10 centimeters per second, you need 100 times the number of photons. So you either need a telescope that is 10 times the diameter, or you need 100 times the observing time. So we would really, I think what would be best at the moment would be dedicated 8 or 10 meter telescopes that are used just with one instrument and just to do radial velocity all the time on 8 meter telescopes. Of course, you tell that to the ESO time allocation committee. We want one of the ESO telescope, VLT telescopes all the time. Yeah, you may or may not have success with your proposal, but in principle, yeah, we are photon noise limited in this, especially if you want to push to lower planet masses. Yeah.
So well, Gina, please.
So I'm really curious about how you detect this very small shift. Like you said the pixel is larger than the actual shift in the lines.
Yes.
So how thick is the width of max with respect to the pixel of the lines?
So yeah, so the basics are we have a spectral resolution of order 100,000. Yeah, this means 3 kilometers per second is one of our resolution elements. Speed of light divided by 100,000. And then the Nyquist theorem tells you that if you have a sampling of about 1 kilometer per second per pixel, that's all the information that you get out. And then it depends on the spectrum, on the signal to noise, what the precision is with which you can determine the center of the line. Basically, determining the center of the line is the full width of maximum divided by the signal to noise. So we take spectra with a signal to noise of 100, and that means that for we can determine the center of a light of light with a line with a precision of about 30 meters per second, 3 kilometers per second divided by 100. So that's a fraction of a pixel. And then, of course, our spectrum has many, many lines. And each one of the lines carries the radial velocity information. So we can, if we average over 1,000 lines, we get another square root of 1,000. And that gets us to 1 meter per second then for the radial velocity precision. The challenge in that, the instrumental challenge is that any systematic shift that shifts all lines doesn't give me that square root of 1,000. Yeah, so if my detector moves by a few nanometers, then all the lines move and I get the wrong radial velocity. And this is why I have to keep my spectrograph so stable. And this is why, in this case at least, we are injecting calibration light at the same time that we observe our the stellar spectrum, so that you only have to measure the relative shift between the calibration spectrum and the stellar spectrum and take out any drift in time, for instance. Yeah, but these are really the instrumental challenges to measure at this level.
So maybe we can turn the discussion now to the properties of the planets. So I think there are at least many interesting things, but at least 4 come to mind. Let's see. I mean, we have talked about presence or not of a characteristic mass. I don't know if you want to flip up your diagram again and just to make a comment on that. You are sensitive to
It's this diagram here. We have discussed this a couple of times now, and so we did an analysis of that didn't asked some of the questions that Jonathan had from the theory perspective. What is clear is in this diagram where we plot the period on the x-axis, the mass on the y-axis, and the probability in the background, we don't see very much that is more massive than, say, about 1.5 Earth masses. Yeah, anything up here we would immediately see, and there's only one object where we see a 3 Earth mass planet. So these low mass stars do not have many super Earths. Yeah, that's different from G stars, where we know that there are many stars that have super Earths. Now, the question is what happens here. And so most of our detections are in this regime where our detection probability is also diminishing. So we are just getting in this regime where we are sensitive enough to find these planets here at around 1 Earth mass. And we did different, okay, I should say one thing more. If you are interested in the mass function and in the dependence of how many do I see as a function of period, this is a log-log diagram. So if you assume a log uniform distribution, this means the same number of planets in the same logarithmic interval of mass, same number between 1 and 10 as between 10 and 100, and the same for the period, then the actually existing objects would be uniform in this diagram. Yeah. Assuming log uniform in both dimensions would mean same number everywhere here existing, and then what you see would be multiplied by the background color. And this is clearly not the case. Yeah. So clearly, it might be the case in the x direction, but certainly not in the y direction in this diagram. There's nothing about here which means this assumption of log uniform is wrong. The mass function must be steeper in this range than log uniform. Now the question is, you can model this with a power law, then you would have a continuous distribution, or you could come with a model that says when I model planet formation, maybe there's a typical planet mass. And so that's a question that we didn't look at when we wrote this paper in any detail, but it's a question that Jonathan brought up, which we might actually go back to and try to find out more. Is there a typical mass of about 1 Earth mass here, and it drops when we go down here, further down here? And so there are many about 1 Earth mass and not many that are a little less. How much can we say about that question versus there are more and more if you go further down here? That is the other hypothesis that you might have if you go to half an Earth mass or 1/10 of an Earth mass. There are more and more and more, and I just can't see them because my background gets black. That's difficult because this also depends then on the details of how we model this detection probability. That is not so easy to find out.
Okay, so then as a function of stellar mass, so you mentioned already the G stars have a characteristic mass in more like several Earth masses. If you bin your data into, I don't know, a low mass sample and a higher mass sample within your M dwarfs, do you notice any systematic shift in planet mass?
Yeah, there are systematic changes, and I don't have any view graphs about that, but this is in the Ribas et al. Paper that I mentioned earlier today, where we looked at the whole sample. So this is a subsample of what we did. We specifically concentrated here on getting the best information we could around the stars with the lowest masses, but this M spectral range extends up to about 0.6 solar masses. So we have more information also about this intermediate range, and we are still collecting data. So we are mostly finished, at least with the first round of going through these very low mass stars, but we are still collecting data to complete the statistics.
Mm-hmm.
And we will do more statistics also on these, on the larger mass range.
Mm-hmm. Mm-hmm. Well, then there's at least 2 more things. So you mentioned resonant chains are quite common. Now, from the Kepler sample, my memory is that the resonant planets and resonants are not that common. So is that a difference that then?
That could well be a difference. Yeah. So these are these are low mass stars, and certainly multiple systems are quite common here. So TRAPPIST-1 is kind of the poster child, and so this is a resonant chain, and YZ City is also a resonant chain. The others could be parts of resonant chains. So on the right side of this diagram, this shows the separation in units that is called the mutual Hill radius of the planets. So if they are closer than about 13 in these units, they are normally too close to each other to form a stable system, unless there are orbital resonances. Yeah, so we can see that those where we know that this is these are very close to each other, and these are very close to each other. So the systems can be stable only because the period ratios are close to a rational number, 3:2, or 4:3, or something like that. The other systems are outside of that range. So the planets are sufficiently far apart for the system to be stable no matter what. Now, in our first paper, the Teegarden system was out here, but then we found another one and it was pushed in here. And that suggests that, well, it can be stable only if it's also part, those planets that we see are not all the planets in the system, but there may be a resonant chain.
Okay.
And this could be the case also for these other systems. If you find more later on with more data, those could also get pushed to the left. So this is a very interesting open question, and it just requires an enormous amount of telescope time because, we need to dig lower and lower in radial velocity amplitude, and as the system gets more complicated, the radial velocity data get more difficult to analyze. So it's much more difficult if you don't have transits. And at the moment, the TRAPPIST system is the only one that we know is transiting, because the chance is just 1 in 100 or so. So for each system that you see, there may be 100 living nearby, and you just don't see transits, and you have to use the radial velocity method to learn anything about the system.
Well, we're almost at the hour, but maybe we are at the hour. Last question, though. Luke and Pally a few years ago claimed this bimodality, I think, in the density distribution, and you showed their diagram. I don't know if you have a comment on that. What the statistics are showing here.
Yes. So these are compilation of data where you have pretty good masses and radii. Some of them are from our data, some from other surveys. Also, I think these brownish dots here, these are all the TRAPPIST-1 planets. And this does look like it's bimodal. So there are some following this line and some following that line. Now, whether or not you see this strong bimodality depends a little on how you select your data. They applied certain criteria on what a good mass and good radius is, and got that. You can apply slightly different criteria what a good mass and a good radius is, and you see some objects lying in here. And you may argue, well, this is if you try to include too many objects with criteria that are not good enough, then the error bars get so large that the distribution gets spread out more. Not everybody who has plotted such diagrams got this very clear bimodality. And I think the bimodality is a bit of an argument that they use, saying that this is really an indication that the upper line here with a different internal composition, namely partly water, and not due to a rocky core with a hydrogen-helium atmosphere, in which case you would expect probably that you have different amounts of hydrogen, helium, and not a clear bimodality. As far as I know, this is a bit of an open question. There are some people who take strong stance on either side of saying this must be a lot of water in the internal composition, or this may be external hydrogen helium atmospheres. Still somewhat open. We need smaller error bars especially on the masses, which are difficult to measure, to get a clear picture here.
Well, the atmospheres as well would help.
Yeah, indications of atmospheres, but these are small planets, so getting direct information on atmospheric composition is certainly a big challenge.
Very good then. So we're at the hour, and so let's thank Andreas again.